What's up guys, today we're going to be going over GPT Neo, the open source implementation of GPT-3. If you recall from my previous videos, what makes GPT-3, and to a lesser extent GPT Neo, so special is the vastly increased size. Here's GPT-3, here's GPT-2. At this time, the largest GPT Neo model is 2.7 billion parameters. While this is still much smaller than 175 billion parameters, having a larger model has its benefits, specifically in the area of fine-tuning and few-shot learning. What we see in this diagram here is the ability of different size models on their impact of learning from one-shot, zero-shot, and few-shot. What this means is how many examples is a model being given to complete a specific task. Those tasks can include, but are not limited to, sentiment analysis of text, and text generation in a certain style, such as generating text in the proper format of a programming language. What we see in this diagram here are three models: 175 billion parameters, 13 billion parameters, and 1.3 billion parameters. What we can see with the 175 billion parameter model is that it is a very good one-shot learner, jumping up from around 10% to around 45% given one example. And as we can see with a 13 billion parameter model is that given one example, it of course does better than zero shot, but it's still not as good as the 175 billion parameter model. And again, a similar story with the 1.3 billion parameter model. You may be asking though, why should I care about this? Well, the takeaway should be is that larger models tend to do better than smaller models. Equally as important is that larger models tend to perform better than smaller models given a limited amount of data. Thus, if we want to fine-tune a model to complete a specific task, in general, we'll be better off using the larger model over the smaller model. By doing so, we can have a smaller data set to fine-tune on, or given a large data set already, we'll obtain better results as we can see here. So that's exactly what we're going over today: how to fine-tune GPT Neo 2.7 billion parameters in order to obtain good results on fine-tuned tasks. Like in my previous videos, we'll be using a Jupyter notebook to run the models. We will not be using Google Colab due to the fact that the resources needed to fine-tune these models are too great for most Google Colab instances. You will want to run this Jupyter notebook on your own high-end PC, or run this Jupyter notebook on a Google Cloud or Azure VM instance with the proper rented hardware. To get started then, we are first going to need to create a Conda environment. Let's call it Conda create in GPT Neo fine-tuned, and we'll do Python equals 3.7. Hit yes. Let's now enter that environment. So Conda activate GPT Neo fine-tuned. Now we're going to need to install Jupyter notebooks. So we're going to do Conda install Jupyter. Hit yes. Lastly, before we enter the Jupyter notebook, we need to install a kernel so that our Conda environment is accessible inside of the notebook. To do this, we'll type the following. Just copy and paste what I have typed here, with the main thing being right here is the name of the kernel, and you're going to look for that inside of the notebook. Before we run Jupyter notebook to launch the Jupyter instance, let's take a look at our folder. We run ls. We see the notebook, and we also see train.csv. This is training data that will be used later. So now let's run Jupyter notebook, and we have started a Jupyter notebook. Let's go ahead and enter the Jupyter notebook that I have prepared for this video. And now the first thing that we need to do is we need to select a kernel. So we'll go to kernel, change kernel, and then we'll select GPT Neo fine-tuned. You may need to now restart the notebook if you're having issues installing packages This may be the fix. You can do that by going here and hitting restart. So now let's get started with the actual notebook. Of course, we must first install PyTorch, so let's go ahead and do that. Once that's finished, let's go ahead and very briefly go over a more naive approach to fine-tuning these models, an approach that I originally explored and had some issues with. So one easy way to fine-tune small transformers is to use a library called Happy Transformer. Happy Transformer is a package built on top of the Hugging Face transformer library. Using it, you can normally fine-tune small transformers very easily. Let's install it and see how that works with our use case here. Okay, and now we're installing it. And we're done. So at this point, we'll now begin fine-tuning the models on the Shakespeare dataset that I previously mentioned, and we're going to do it on my RTX 3090 that has 24 gigabytes of VRAM. So what we're doing now is we're going to set a CUDA visible device to 0 so it only runs on my RTX 3090. That's done. So what we're going to do here is, at first we're going to train on the smallest GPT Neo model. That is the 125 million parameter model, and we're going to fine-tune that model with that trained CSV file containing Shakespeare. So let's go ahead now and run this segment. And it's going to be loading the model here soon. So as we can see right here is we see an NVIDIA SMI, and we see the VRAM starting to get filled up. So now it's at 2 gigabytes. And now it's training, and we see it jump to 10 gigabytes here. What this means is that in order to train even just the 125 million parameter model with a batch size of 1, we need a GPU with at least 10.5 gigabytes of VRAM. This unfortunately eliminates many cards from being able to be used to train even the 125 million parameter model. This would eliminate the RTX 3080, 3070. Ironically, the 3060 would be able to do this. The RTX 3080 Ti would be able to do it. The GTX 1080 Ti would be able to do it. And the 2080 Ti would be able to do it. And of course, the RTX 3090 would be able to fine-tune the model. But that is it with regards to consumer cards. So at this point, let's go ahead and stop this early. We know how much VRAM it uses, and we don't want to use the 125 million parameter model anyways. And now what we need to do is we need to run this segment right here. What this segment's going to do is it's going to clear the VRAM usage for the GPU and will allow us to again run the above code segment, but this time we're going to see how it performs with the 1.3 billion parameter model. So now we're going to run this section here, and now our VRAM should be cleared. So now let's go back up to the code block that was training the 125 million parameter model, and let's change it to 1.3 billion parameters. Spoiler, this is going to error out, but let's just see what it does exactly. So now I'm going to run this here, and let's keep an eye on the GPU VRAM usage. Should be loading here any second now. Okay, it's at 8. So it's 8 before we start running. Now it's at 24, it maxed out, and we will have an out of memory error if we scroll down. Let's see it. Right here, out of memory. So as we can see, while Happy Transformer makes it very easy to train small transformers, it is insufficient for the 1.3 billion parameter model, and even more so for the 2.7 billion parameter model. And as I talked in the beginning of the video, we want to fine-tune on large models because large models are able to learn better and with less data compared to smaller models. So then, Is there any hope that we can train these larger models with consumer-grade hardware? Fortunately, the answer is yes, but we need to move to a different library. We need to use DeepSpeed. First, we need to clone the DeepSpeed repo, as we must build some optional items in the package from the source. DeepSpeed is a deep learning optimization library by Microsoft that allows researchers to more easily run and train larger models that they otherwise would not be able to do. So, by running this block here, we'll go ahead and clone the repo. And that's done. And so now if we ls our folder structure, we see that DeepSpeed is located in the folder. We now want to cd into DeepSpeed, and now we've done that. Again, if we ls the folder, we'll see the contents of the DeepSpeed repo. So now the next step is to install DeepSpeed from source, using a flag that's in the documentation to ensure that all needed ops are installed. To do this, run this command here, dsbuild ops equals 1 pip install period meaning the current directory. So let's do that now. Installing DeepSpeed from source may take a while. On my computer it took over 6 minutes, but just wait it out and you should be good to go. Once we have DeepSpeed installed, the next thing we're going to want to do is run dsreport. So what dsreport does is it lets you know if the compatible ops are installed on your PC. I'm not quite sure which all ops need to be installed, but I can tell you for sure that CPU Atom needs to be installed, Ninja, as well as Transformer. I can tell you that Async IO does not need to be installed. These are the ones that are compatible with my system, and with these ones installed, I can get DeepSpeed to work. After we do that, we need to now download the repo that will actually be fine-tuning GPT Neo using DeepSpeed. So let's first exit the DeepSpeed repo by doing cd ... We can run ls now to see that we're back on the above folder. And so what we need to do now is we now need to clone the repo for fine-tuning. To do this, we'll just simply run the code block here to download and clone the fine-tune GPT-2XL repo. And now that it's done, we can see that it is in the main folder. So now let's enter it by doing cd fine-tune GPT-2XL. So the last thing that we need to do now that we're inside of the fine-tune repo is we need to download and install datasets, which is used in this repo, and we'll do that. So now at this point, we're able to fine-tune GPT Neo, including the 2.7 billion parameter model, as well as other GPT models such as GPT-2, GPT-2XL, etc. So for GPT Neo 2.7 billion parameters, we need a high-end machine. The README says that roughly 70 gigabytes of RAM is the minimum required for it, along with roughly 16 gigabytes of VRAM on a GPU. GPT Neo 1.3 billion and other smaller GPT-2 based models don't have as high as requirements. This can be rented for an okay price from a cloud provider if you don't have a powerful enough machine. Normally the cost to rent a machine to do this for a month would be a couple $100, but to fine-tune a model, you'll probably only need to rent it for a couple hours, so it's probably around 10 bucks at most. Personally, I had to upgrade my PC from 64 gigabytes of RAM to 96 gigabytes of RAM just in order to make this video and do some cool things with GPT Neo 2.7 billion. But as I've gone over in my previous videos, once you have a trained model, you can run that trained model on much lower end hardware, even with just a CPU, as long as you have a decent amount of RAM. So now let's go ahead and fine-tune GPT Neo 2.7 billion with the Shakespeare dataset that I mentioned earlier. The flags that we're going to be using here are the ones in the README that I highly recommend you read yourself. And this will supposedly work on 16 gigabytes of VRAM and roughly 70 gigabytes of RAM. I can personally guarantee that it works on an RTX 3090 and 96 gigabytes of RAM, but as you can see, you almost certainly can get away with much less. Once we run this code block here, it'll take a few minutes to get started, but once it does, it will take a couple hours to fine-tune the model, depending upon several factors such as number of trained epochs, batch size, parameters and flags that you can set on your own depending upon your own hardware and requirements. Let's go ahead now and run this code block and check out how it's affecting my computer, how much RAM it's using, how much VRAM it's using, and see what the impact is of running this model. So now I've just started the process of fine-tuning the model. I'm going to now skip ahead until it actually starts training so we can truly see the impact that training the model is having on our hardware, what resources we're using. We're now into the process of training. We see we're on step 8 of 178, just the way that the data is batched up with this model. We can see that we are using 19 gigabytes of VRAM and 63 gigabytes of RAM. The reason that we're using 19 gigabytes of VRAM is due to the fact that we have the resources available. If we had less VRAM, my understanding is that we would be using more RAM, although I could be wrong about that. The last thing we're going to do with this notebook is I'm going to kill the training process and then reload the training process, but with different parameters so that we can further reduce the hardware demands. I have now restarted the notebook and we can now change some of the flags. One of the more obvious ones is that we can change the model we use from 2.7 billion. We can change that to 1.3. So now let's run that and let's see what kind of performance impact on our hardware we see. So right here we are training a GPT Neo 1.3 billion parameter model. We can see it's using significantly less RAM, using 38 gigabytes. It's also using significantly less VRAM, using 13 gigabytes. So we can see that, of course, the 1.3 billion parameter model requires less powerful hardware to fine-tune, and you can definitely do this on more mid-range hardware or cheaper hardware that you can rent in the cloud. In both of these cases, whenever we're training a model, the output of the model using the flags that we ran will be in the fine-tune folder it'll create. By default, the flags that we use, it will only save the last evaluation step, so when it's done. But you can use flags that are described in the README to have it save every epoch or every 2 epochs or etc. So this is where you will find the trained model that you can use for later. To end the video, I want to briefly go over the GitHub page and the README. Here we can see some of the steps to create a VM that I talked about if you don't have the hardware required. And you can feel free to follow that or ask questions and I'll be happy to help. Here's some steps to fine-tune a GPT 2X, which is 1.5 billion parameters. So if you're interested in that, you also can do that. It's very similar to what we did. In fact, the only difference would be instead of running the commands that we have in the Jupyter notebook, you'll run these. Here we can see some steps on how to generate text with your fine-tuned model. This is for GPT 2X, but it's similar for GPT Neo. Here's the steps on how to train GPT Neo, and then here is the steps to generate text with your fine-tuned model. I plan on making another video on how to best generate text using your fine-tuned model. Though this will work, I have found that there are some few things you can do just to make life easier to play around with your fine-tuned model. And lastly, but still very importantly, is the optional configurations. I recommend looking at the training arguments that you can find the link on the bottom of this README. There are optional flags that you can append to this area here for training that will allow you to change how often a model is saved. Is it saved every 10 epochs or 5 epochs or whatever? Just things to make it easier to get the result you're looking for. When training the model, you're going to want to keep training until your evaluation loss is the lowest that it can be. At some point, your evaluation loss will start increasing again, so it's a good idea to stop once you notice that the evaluation loss has reached its minimum and is starting to go up. For me, training on a custom data set not the one provided, I found that it takes roughly 4 epochs to get the best result. So that's something you ought to play around with to find what works best for you. So at this point, I'm going to end the video. I hope that this video has helped you be able to fine-tune these very cool, very large models. For future videos, I plan on making a video on how to best use your fine-tuned model to get the outputs you want. I also plan on making a video on fine-tuning a model on your own custom data set rather than the provided data set. So feel free to subscribe if that interests you so you can find those videos when they're published. As always, thanks for watching. Please like and subscribe if this helped you out, and please have a great day.